Hello everyone, today I'm going to solve a problem regarding set builder notation. We need to list the distinct elements of set B. The set is defined as x belongs to the set of integers z, such as xy equals for 15 for some integer y. X belongs to the set of integers z, such as that x times y equals for some integer y. First, let's analyze the condition xy equals to 15. This means that x must be a divisor of 15. Since y must be also be an integer, x can be any integer that divides 15 without a remainder. Let's list the positive divisors of 15. They are 1, 3, 5, 15. Right. Critically, the problem states that x and y belong to z, which includes negative integers. Therefore, we must also include the negative divisors. So, like, I just wrote it like that. Negative divisors are -1, -3, -5, and -50. Right. Conclusion. By listing all these values, we find that the set contains 8 elements in raster form. The set is like -5, -5, -3, -1, 1, 3, 5, and 15. So that is our final answer for part B. Now let's look at task D. The set is defined by the sum x plus y, where x is an element of the set -1, 0, 1, and y is element of the set 0, 1, 2. To find all possible elements, we need to calculate the sum of every possible pair of x and y. Let's do it. If x equals to -1, we add it to each y, like -1 plus 0, and -1 plus 1, 0, -1 plus 2 plus 1, like, and if x equals to 0, we get do it like we add to 0 to integers of y, like 0 plus 0 equals 0, 0 plus 1 equals 1, 0 plus 2 equals 2. And if x equals to 1, we do it like, just repeat it. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3. Now we have a list of results. I just write it, the results here. We got -1, 0, 1, 0, 1, 2, and 1, 2, 3. No. However, the definition of a set requires us to list only distinct elements. This means we remove any duplicates. So result will be, we'll just remove this one, and one, and this one. So the answer will be -1, 0, 1, 2, and 3. Let's move to exercise 7. First one. Statement A. The empty set is a subset of empty set. This is true. Why? Because by the definition, the empty set is a subset of every set, including itself. Statement B. The empty set is a subset of the set containing the empty set. This is true. Why? Because again, the empty set is a subset of any set you can imagine. And problem C. The statement C, the empty set says the empty set is an element of the empty set. This is false. Why? Because the empty set has no elements at all, so nothing can belong to it. Problem D. Just write it like that. Statement D, the empty set is an element of the set containing the empty set. This is also true. Why? Because here the empty set is explicitly listed inside the braces. So the result will be true. And problem statement E is just 1, 2. 1, 2, 3. It says this set 1 and 2 is not a subset of the given set. This is false. Why? Because both 1 and both 1, 2, it has like the same elements. So the both first and second sub elements of the larger set. So 1 and 2 is a subset. So result will be false. Problem F, statement F. It says the set 1 and 2 is an element of this set. This is also false. Why? Because the set contains 1, 2, 3 and the set 1, 2, 3, but it does not contain the set 1, 2 as a single item, so it will be false. Problem G. It says statement H, it says 1 and 2 is an element of the set of the set. This is also false. Why? Because the set contains a box inside of the box, so but it says like it has box inside the box, but not the set 1, 2 itself, so it will be false. Statement H. Statement H, it says 1 and 2 is an element of the set. So it's also false. Why? Because there is the same problem, same meaning. So let's continue. It's statement I. It is 1, 2. 1, 2. So this is problem A. It says the set containing the set 1, 2 is a subset of the set. This is true. Why? Because the object inside it, which is the set 1, 2, is an element of the larger set, so it will be true. Let's continue. Here's the second task of second section. So firstly, we need to find intersection, union, and Cartesian product of these sets. So first I want to find intersection of S and T. So we'll just write the same both elements that both contains both of the sets. So S and T equals is we will check which are the same elements. So here is I see square, oh no, root of 2, yeah, root of 2, and 25, yeah, 25. So it's intersection of these sets. So secondly, we need to find union of these sets. Equals, I'll just write it here. You will unite of both of the sets. One thing, as there shall not be no duplicates. Just write here. And 4, 6, and 3 dividing by 2. So this is union of the sets, and we need to find Cartesian product of this both of sets. So I'll just write it here. Yeah. Finally, for the Cartesian product, we pair every element of T with every element of our intersection set. So it will be equals to 4 and root of 2. I just write here. 4 and 25. And root of 2. And 25 plus 25. And root of 2 and root of 2. Root of 2 and 25. 6 and root of 2. 6 and 25. Let's see here. And 3 divided by 2 and root of 2. Just 2 and root of 2. And almost got it now. Oh no, there is also 1. 3 divided by 2 and 25. So this is our answer of every problem we needed to solve. That's it. Let's move on problem B of task 2. In the second problem of task 2, we need to find these problems, and let's do it. So I'll just write the first problem. This says of here problems. Just write it. Zero numbers and zeros. P. Yeah, and the second is root of 2 and 3 over 2. And finally is the set of 2. This will be 4 and 25. 4 and 25. For part B, we look at intersections and unions with the set of integers z. The intersection z and c yields on the whole number in S, which are 2, 5, and 25. The union z and S includes all integers plus the non-integer elements from C, S, like p and square root of 2. So yeah, that's it. Last two parts, we need to define, find the noticeables and differences. So as you look, the sets are equal. This demonstrates the distribute law. I can write distribute law here. Distribute law. In parts of the set, we verify the distribute laws of set theory. You will notice that the results are identical. This proves that intersection distributes over union and vice versa. Let's continue. So here's the task 3 of second section. Given A, this A. And firstly, we need to find A plus B. Section of A and B are elements of A. So let's find it here. -1 plus 2 is 1. 4 plus 5 is 9. 0 plus 0 is 0. 6 minus 5 is 1. And 5 plus 1 is 6. And 4 plus 3 is 7. For this task, we take each ordered pair A and B from set A and calculate the sum of A plus B. After calculating, I just calculated, and I will list the answers with no duplicates. Our set will be 0, 1, 6, 7, and 9. So this is the final answer of task 3, part A. Let's move into part B. So I'll just write it here quickly. We need to find here A. For sum B. So in this problem here, we need to the first task, we will first check the components of A. They are -1, 4, 0, 6, 5, and 4. Yeah. So I will filter it we will not take the negative integers over. We'll take only over 0. So the answer will be the result of this distinct will be no duplicates again. It will be 4, 5, and 6. So this is answer of B. And let's move on problems C. So let's continue. We will examine the second component of B of each pair. We need to find which of these are squares among our values. Only 0 and 1 are squares of integers. So wait, I will check of B integers components. They are 2, 5, 0, -5, 1, and 3. And we will check if B is a perfect square. K of square 0 equals 0. Okay. So this is perfect square. And second is 1. This is also perfect square. And the final not perfects are 2, 5, -5, and 3. So these elements are not perfect square. Thus the set contains 0 and 1. So the answer will be 0 and 1. So let's continue to section 3. We ended our second section. This is all tasks. Let's move into second section. Well, let's start our third lections tasks. So the first one is for the part B. The relation is not. We need to find if it is reflexive, symmetric, and semi-transitive. So let's check it. First is I want to check if it's reflexive. So I will check it from here. No, so to be reflexive, we need to be the same element, same x for all elements, and we need to like 2 and 2, 3 and 3, 4 and 4. They are missing. So if it's not reflexive, yeah, so it's not reflexive. Yeah. Second, we need to find if it's symmetric. I want to check it. There is like, it's not like also not symmetric because we have 3 and 4, and not 4 and 3. It fails antisymmetry of 1 and 2 and 2 and 1 cycle, so it's not symmetric. And we need to check if it's transitive. So it's also not transitive because we have 2 and 1 and 1 and 2, but required result 2 and 2 is missing, so it will be 2. So it will be not transitive. Yeah, just check that. And we solved the problem B, and the second is problem D. So here is, we check so first I see that it's reflexive for any number a. A square is equals a square is always true, so it's yes reflexive. And it's also symmetric, I say, by the properties of equality. If a square and b square equals, then b square and a square is also true, so it will be symmetric. However, it is not antisymmetric because minus 2 and minus 2 and 2 and minus 2 and 2 and 2 and minus 2 are in relation even though the numbers are different. It is so it will be not antisymmetric. Yeah, let's check it. Transitive, let's check transitive. Yes, it's transitive because making this an equivalence relation, like a square equals to b square and b square equals to a square equals to c square. So it's transitive, yeah. So let's check the third problem f. So let's write it here. It says a equals to z are part of, yeah. So let's check it if it's reflexive, symmetry, and symmetric, and transitive. Now, for the first moment, this condition is equivalent to a minus 1, I minus b equals to c minus d. So yeah, it becomes reflexive. Yeah. For any pair a and b, and a minus c equals to b minus d becomes a minus b minus b, which is 0 equals to 0. So it's, yes, reflexive. And let's check if it's symmetric. Yes, it's symmetric if because a minus c is b and minus d, then c minus a equals to d minus b by multiplying by number minus 1. So it's symmetric. Let's check if it's antisymmetric. So it's not antisymmetric. It fails antisymmetric because different pairs can have the same internal difference. The pairs 2 and 1 and 3 and 2 both have a difference of 1. They relate to each other, but the pairs are not equal. So it's not antisymmetric. Let's check if it's transitive. If the difference for pair 1 equals pair 2 and pair 2 equals pair 3, then pair 1 equals pair 3. So it will be transitive. So let's continue. So here's the last problems of task 9 of third section. So let's start from each. Let's check it if it's reflexive. In part H, the sum must be 10. Like 1 plus 1 is not equal to 10. So 1 and 1 are not part of R. So it will be not reflexive, yeah? And let's check if it's symmetric. It's symmetric because by the way, this is only reflexive for the number 5, so property fails for the whole set. Yeah, let's check it if it's symmetric. If x plus y is equals to 10 and then y plus x equals to 10. Yes, it's symmetric. And here it is. Let's check it if it's antisymmetric. And the answer is no, it's not antisymmetric because 4 and 6 and 6 and 4 are both in R, but 4 and 6 they are not equal, so it's not antisymmetric. Let's check if it's transitive. This is also not transitive. It fails transitivity because as we see the pairs are 7 and 3 and 3 and 7. But 7 and 7 are not union of r because 7 plus 7 is not equal to 10. Here it is. So let's move into the next problem. Here I see that it's reflexive, like any natural number divided by itself is 1, which is an integer, so it's reflexive. Let's check if it's symmetric. No, 4 divided by 2 is an integer, but 2 divided into 4 is not an integer, so it's not symmetric. Let's check if it's antisymmetric, and it's antisymmetric. In natural numbers, if a divides b and b divides a, then a must be equal to b, so it will be antisymmetric, yeah? So let's check it if it's transitive. And yes, it's transitive because if a is a multiple of b and b is a multiple of c, then a multiple of c, like just right here, a multiple of b, then b multiple of c, then a will be multiple of c. Yes, so it's transitive. Part G is divisibility relation on natural numbers. It's reflexive, antisymmetric, transitive. This makes it partial ordering. So let's check the last problem of this task. And it is not reflexive because dividing by 0 is not undefined, so 0 and 0 is not in the relation, so it's not reflexive. And it's also not symmetric because 4 divided by 2 is an integer, but 2 divided by 4 is not. It's not antisymmetric also because 2 dividing by minus 2 and minus 2 dividing by 2 are both integers, but 2 is not equal to minus 2. So it's not antisymmetric because of negative values like 2 and negative 2. And let's check if it's transitive, and the answer is yeah, it's transitive because the product of two integers, the quotients is still an integer, so it remains transitive. So let's move on. Task 11 of third section. So here is exercise 11. The first problem is already given is S is a set of containing at least two elements A and B, and A and B is union sets of S. We need to determine if each relation R is reflexive or antisymmetric or transitive. So let's start. The first one is reflexive because for any x union of A, it is true that x equals 0 union of x, therefore x and x are R. So it's reflexive. Let's check if it's symmetric, and it's no, because let x be an A and y is A and B, then x and y, but y and x are not this part of R, so it's not it will be not symmetric. And it's asymmetric because if x and y and R and y and x are also R, then x and y and here x by the definition of set equalities, this implies x equals to y. So it will be transitive, right? So, and let's check it if it's transitive first. Yes, it's transitive because if x and y and right to r and here y then x implies y and y implies z. By the properties of the subsets, x implies z, therefore x, z are part of this. So summary, this is a partial order relation of this first problem. So let's move into part B. Just write the given problem which we need to find. So this is a proper subset relation, x implies y and x not equal to y. Let's check if it's reflexive, and it's not reflexive because for any x are part of A, x not implies an equal x, because a set cannot be a proper subset of itself. This is irreflexive, how to say, irreflexive here. The second is it symmetric? Let's check it. If x and equals to a and y equals to a and b, then x implies a, but y does not implies an equal x, so it's not symmetric. Let's check if it's antisymmetric, and like for x and y that are relation, and y and x relation, to be true, we will need x implying y and y not x, which is impossible since premise is always false. The statement if is fallaciously true, so it will be antisymmetric. Let's check if it's transitive. If x equals to y, y and y equals z, then x not z. So yeah, it's transitive. This is a strict partial order. Let's move into the last problem of this task, and we will move into the last fourth section with the last task. So let's continue. As I see here, this is a disjoint sets relation, and yeah, let's check it if it's reflexive, symmetric, antisymmetric, and transitive. Is it reflexive? No, because let x be an a, and then x equals to a is not equal of no. So a and a are not into relations, only the set relates to itself. Only the empty set relates to itself, I mean. So it's not reflexive. And let's check if it's symmetric. If x and y x, it's not. Yes, it's symmetric. Intersection is cumulative. Therefore, if x and y is intersection of relations, then y and x are. So so it's reflexive, symmetric, and let's check if it's antisymmetric. Let x be again a. So and I be and b. Then let's check this. If x and y, then and here, so it will be not antisymmetric because x and y are relations and y and x and is not in a relation, but x and y are not equal. So let's check if it's transitive. Yeah, firstly we need to give an example. So let's check it if x and y are a and b. So it will be x and y are the part of relations. And secondly, let's check y z. So it will be a and it will be also part of relations. And let's check Discrete. Equals to, so it will be x and z. So it not will be transitive. Summary, this relations is only symmetric. So let's move into our last exercise, last section, fourth section, ninth exercise. So this is the final exercise. We need the proof of equivalence relation firstly. So just write it here. Reflexive, let's check if it's reflexive. Which is, so 3a plus a is equals to 4a, which is always a multiple of 4. Symmetric. Then check, well, let's from the checking here, it always will be multiple of 4, so it's symmetric. Let's check it if it's transitive. If 3a plus b equals to 4g and 3b plus c equals to 4k, then 3a plus 4k plus c plus k. So this means 3a plus c equals to 4d minus k, which is a multiple of 4, so it will be transitive. Let's check equivalence class of 0. From the moment I see it here, the solution will be answer will be minus 8, minus 4, 0, 4, and 8. And that's equivalence class of 2 are minus 6, minus 2, 2, 6, and 10. The last problem is quote and set guess. The classes appear to be based on reminders when divided by 4. So answer will be minus 4 equals 0, 1, 2, 3. So this is the final answer.